you, and thanks for the invitation to come here. I'm excited to talk a little bit about some of my work studying the ocean right in front of glaciers in the northern hemisphere, so focused on Greenland and Alaska. I'm going to be talking about some work from my group, including some work led by current and former members, including Jesse Cusack, Bridget Oval, Duncan Wheeler. I'm currently based at Tufts. I was recently at Rutgers, and my group members are sort of spread between the two. And so to start, some big picture motivation. We've already kind of covered a lot of this, most of you already know this, but to put a little bit of a Greenland Northern Hemisphere spin on ocean-glacier interactions, this is a map of mass loss from Greenland overlaid on the currents around Greenland, a schematic of the currents around Greenland. And the mass loss from Greenland is, of course, causing sea level rise and an increased freshwater flux into the ocean. That freshwater flux can have impacts on ocean circulation from a whole variety of scales, kind of locally in fjords, on the continental shelf, and potentially impacting things like deep convection and the overturning circulation. In the other direction, ocean warming around kind of offshore Greenland on the continental shelf coincided with this acceleration, thinning, and retreat of many outlet glaciers. And so this has led to a hypothesis explored in many, many papers, more than I've listed here, that ocean warming has increased submarine melting and triggered glacier acceleration, thinning, and retreat. But this hypothesis has been really difficult to test because we have effectively no direct measurements of submarine melting, let alone how it's varying over the decades. And so in the absence of those observations, studies have to rely heavily on theories and ways to estimate melt based on other things we can estimate more easily from observations, models, reanalyses. So this is one example of a really nice paper led by Donald Slater, where he's trying to estimate how much of Greenland tidewater glacier retreat is driven by submarine melting. And he does this nice inventory of all the glaciers around Greenland and estimates that over 50% of the variability in glacier terminus position can be explained by variability in submarine melting. But to assess this sort of important question of how much the ocean is actually driving these glacier changes, they have to rely on a relationship like this, where melt is assumed to scale with ocean thermal forcing, so how much the ocean temperature is above freezing, and subglacial discharge, the freshwater draining at the bed of the glacier to the 1/3 power. And this comes out of some theory that I'm going to dive a little bit deeper into. But importantly, kind of this understanding of how melt is impacting glaciers really comes primarily from untested theory. So before I get too much into that, I want to just set the scene for sort of a tidewater glacier. So this is in contrast to the ice shelves that we've heard a lot more about. I'm thinking about relatively well-grounded glaciers grounded glaciers with relatively vertical termini, where you have these two sources of freshwater coming in. I'm going to call it submarine melt, referring to the melt that's where the ice is directly melting into the ocean, which of course takes heat from the ocean to drive that melting, and then subglacial discharge, which is from the freshwater primarily formed at the surface of the glacier that drains to the bed and enters the ocean like a river, but well below the surface. Okay, and so you have these exchanges of heat from the ocean to drive melting, and these two sources of freshwater coming into the ocean. My work explores these kind of heat and freshwater exchanges across a range of scales, from the kind of continental shelf through fjords. But what I want to focus on today is sort of the smallest scale processes right near the ocean ice boundary layer, where you have some sort of what I'm going to call sort of inner boundary layer, where we expect, if you think this boundary layer is driven by shear instabilities, then you expect your melt rates should scale with the near ice velocity as well as the near ice temperature and salinity. And then if you're in an environment where you have a lot of buoyancy from this freshwater, you might expect that near ice velocity is going to be from plumes. All these sources of freshwater are buoyant when they enter the salty ocean, they're rising. And so plume processes are going to play an important role in controlling sort of the mixing and the initial export of all this freshwater as it enters the ocean. Okay, but importantly, these freshwater fluxes are really poorly constrained by observations, both the discharge and the melting. This is sort of in contrast, well, somewhat in contrast to Antarctica, right? Like when Helen shows images of satellite imagery using to back out basal melt rates, you can get somewhere with that. You can also drill through ice shelves to get measurements at the ocean-glacier interface through ice shelves. But in these tidewater glacier systems, it's sort of a different set of challenges. And we really are lacking kind of almost any observational constraints of these two freshwater sources coming into the ocean, and importantly, their relationship. So just a visual for why we don't have these observations for the most part. This is just a drone video from one of my field sites I'll be talking about. Calving event. Till, I'm going to be looking to you to incorporate this into your calving parameterizations. And so in the absence of these observations, right, the field lies heavily on kind of a two-part theory or parameterization. The first part on the right-hand side here is a melt parameterization, often called the three-equation melt parameterization. There's variations on this. And the basic idea is it's trying to represent that turbulent transfer across the boundary layer and across the viscous sublayer that controls the melt rate. And the basic things I want you to notice are that the melt rate M is proportional to W, the velocity. That's this idea of a shear-driven boundary layer where the melt rate scales with the near ice velocity. And sometimes this is used on its own. If you think you know your near ice velocity, temperature, and salinity, then maybe this is all you need to know to estimate your melt rates. But most often, and particularly in tidewater glaciers, this is coupled to buoyant plume theory to actually help you estimate these near ice velocity, temperature, and salinity. And this is probably more equations than I should put on one slide, but I just want you to get the basic picture that buoyant plume theory is this, well, first of all, it's a kind of well-developed theory dating back to the 1950s, has all sorts of applications for things, all sorts of applications for buoyant fluids rising through stratified mediums used for things like volcanic eruptions. But in this case, it's applied to these glacier plumes with simple conservation equations for mass, momentum, heat, and salt. But really importantly, it relies on entrainment parameterization that relates the velocity of the plume to the entrainment into the plume with entrainment coefficient, alpha. Okay, and so this makes a really nice, when you couple these two things together, it's really a nice self-contained model where you can predict your melt rates as a function of your subglacial discharge flux and your kind of ambient ocean conditions. And it's used kind of throughout the literature studying tidewater glaciers and ocean glacier interactions in all sorts of different ways. It really sort of underlies a lot of our understanding of these ocean glacier interactions. One example of how it's used is in ocean models where you can't resolve plumes and melting. This kind of coupled plume melt theory is used to force the boundary of ocean models, kind of at the fjord and regional scale. In the other direction, sometimes this plume melt theory is used to force melt rates on glaciers. And it's also just used kind of in and of itself to develop our intuition and studies like the one I mentioned at the beginning from Donald Slater. So really our kind of current understanding of ocean glacier interactions really hinges on this theory and arguably is only as good as this theory. So before I show some observations, I want to sort of prime you with a few things we should maybe be skeptical about when we look at this framework. So the first piece, when you think about the coupling between these two, where you use buoyant plume theory to give you a velocity to then solve your melt rate, you're assuming that your plume velocity is the only velocity and source of kinetic energy near the ice face. But as you might imagine, there can be other things going on, not just these buoyant upwelling velocities that could drive shear-driven turbulence across the boundary layer. And so, yeah, what I'll get into showing a little bit of is kind of some modifications trying to account for other modes of velocity, not just these vertical plume velocities. Another big kind of assumption behind applying this plume side of things is you have to make assumptions both about your entrainment coefficient, but also you have to make an assumption about the geometry of your plume. And depending on whether you model your plume as sort of a point source or a more distributed line source, that's going to be a really important control on how much entrainment you have, because the surface area of the plume will be a big control on how much you entrain into it. And then finally, there are these transfer coefficients that show up over here that relate your velocities to your melt rates. And these are really untested at tidewater glaciers. They've been kind of derived and tested to some extent under sea ice and ice shelves, which are horizontal ocean ice boundaries. And there's good reason to believe that when you're looking at a vertical ice ocean boundary, those the dynamics that are kind of being captured by that coefficient might be different. Like for example, in a horizontal ocean ice boundary, the buoyancy input from melt is stabilizing, whereas here you can get convective instabilities as this meltwater comes in. So I'll sort of, as I show some results from our new observations, I'll be sort of touching on all of these things that you've now been primed to think about. Okay, with the last piece of context I need to give you before I show some of this, these field results, is that there are actually sort of two types of plumes across these termini. Subglacial discharge plumes emerge where you have localized sources of fresh water draining at the bed, and you expect, large source of buoyancy should be large velocities, which should be high melt rates. Away from discharge plumes, we have this sort of ambient melt regime where the only buoyancy is from the melting of the ice itself, much smaller buoyancy, smaller velocities, and presumably much lower melt rates. And so when you apply this sort of standard plume melt theory coupled together to estimate melt across the whole terminus, as most studies do, what you get are these kind of expectations that sort of permeate the literature. One is that discharge-driven melt is sort of assumed to be much larger than ambient melt, again, just because of these much higher velocities swamping, creating these high melt rates, and that when you kind of apply this across the whole terminus, you typically find that the total melt scales with the thermal forcing and the discharge to the 1/3 power. That's what I kind of started with, underlies a lot of studies. But as I've said now a couple of times, this is all basically untested with observations until the past few years. Okay, so I want to show kind of a few results from two different projects. I'm going to largely focus on this project on the right in Alaska at LeConte Glacier, but I'll show a little bit from Umanak Bay, Greenland, two glaciers in Umanak Bay, West Greenland. These are both projects that culminated in big field seasons in 2024. It was a busy summer last summer. And actually very different focuses for these projects. The Greenland project is actually focused on sediment transport and how you build moraines at the terminus of glaciers, whereas our Alaska project is much more focused on the submarine melt dynamics that I'm talking about today. But what these projects share is kind of how we've been using autonomous platforms to get measurements kind of progressively closer to the ice face. This Alaska project is sort of the culmination of 6 years of field campaigns, getting closer and closer to the ice-ocean boundary layer with evolving technology. But in both cases, we're kind of using ROVs and autonomous surface vessels to get these observations to test our understanding of plumes and melting and what's sources of kinetic energy across the ice face. So I'm going to briefly sort of talk through some of the platforms and technology we're using in each of these projects. To start with the Alaska project, we have our autonomous surface vehicles that survey right up to the glacier face, often running into it. The first generation of these in this project were autonomous kayaks, and the latest generation are remote RIBS, rigid hull inflatable boats with sort of very similar setup where we have a ADCP that measures velocity, sort of shown schematically with the blue thing there, and then profiling CTDs, measuring temperature, salinity, pressure. And these platforms are developed by Jonathan Nash and his team at Oregon State University. And what we've done here is not only kind of surveying in sort of more traditional ways with ADCPs and CTDs from the surface vessel, but we also attach a profiling ROV shown here on the right. It looks a little janky, but it actually works pretty well. It's basically a frame with an ADCP pointing towards the ice. We lower it. It has thrusters to keep it pointing at the ice as we lower it. And it gives us kind of velocity measurements, not just vertically like these ones, but approaching the ice face. Okay, and so to give you a picture of what this looks like, this is the autonomous RIB this past summer, driving up near the ice face. You can see we're kind of driving into the surface expression of the plume, where it's boiled up to the surface, and it's starting to spread radially, and we're really fighting against the current. That's about like 1.5 meters per second, probably there. We can go faster. I'm not quite sure why we weren't throttling up there. But you can see this is the CGD actually that's been just dropped off the stern of the boat, and then we have ADCP and as well as actually a multi-beam sonar measuring the ice face morphology. Okay, but it looks a little glamorous. We're sending our autonomous boat up to the ice face, but we're not just sitting drinking our coffee. We actually spend most of our days driving around in a little crew-operated boat. And because it's Southeast Alaska, it's always raining. So that is my colleague, Nicole, sitting under a shower curtain that we're using to keep our computers dry, and we drive back and forth in this ship. That's a little bit of an overstatement, making sections back and forth across the glacier to sort of complement the near ice observations. And we do all this based from an actual kind of more legit ship. We kind of use as almost like a floating hotel where we deploy all of these smaller vehicles, both the crew-operated ones and the autonomous ones, and send them up to kind of varying distances from the ice face. And what I'm highlighting here are kind of the components that I'm focused on, the velocity and temperature and salinity profiling, the kind of measuring the dynamics at the scales of kind of meter to kilometer in front of the ice. But my colleagues listed here have also led the deployment of multi-beam surveys of the ice face, melt stakes, drone surveys, and I'll kind of touch on a few of these things as we go through, but I'm mostly focusing on what's kind of in these schematics here. And then I'm just going to briefly mention the Greenland project. Again, different focus, but some sort of very complementary data sets where we've used NUI, or near Earth under ice, so the same kind of guts that Catherine was talking about a couple talks before. And this was actually, I think, the last deployment of NUI before it was taken apart for the SAMs, what's it called? The under ice shelf mooring development. So same deal where it has a fiber optic cable that goes back to the ship, and we deployed this in West Greenland. And one has many great capabilities, but one thing that it really let us do is get right up to the grounding line and get these measurements down at the grounding line depth, really high resolution in a way that you kind of can't from the packages that I just described that we've been using in Alaska. Oh, and there's NUI driving off. This is overall kind of a much bigger operation, bigger ship, bigger ROV. And here as well, this is part of a much larger project focused, as I mentioned, on the sediment dynamics. So I'm looking at sort of the sediment transport within the water column by the plumes. My colleagues are looking at all sorts of kind of marine geology in front of the ice, as well as the ice itself. And so a big interdisciplinary project where, again, my schematic is really just highlighting the part that I'm focused on and that I'll mention today is the velocity and water property measurements of the physical oceanography. Okay, so what I want to do for the last bit is just show you some of the results that are coming out of some of these observations, mostly from LeConte Glacier, again, in Southeast Alaska. I want to mention briefly some kind of early results from this project. The first paper led by my collaborator, Dave Sutherland, where he used multi-beam sonar surveys of the ice face and kind of watched it evolve over time, tracking its evolution, and found that melt rates are much larger than theory predicts across large swaths of the terminus. And this was sort of complemented by some analysis that I led using the autonomous surface vehicles to survey the ambient melt intrusions. So in the kind of regime away from the energetic subglacial discharge plume, you have these little plume intrusion features, and we surveyed them. And what we found is that when you kind of put these results together, there's a lot more melt than kind of standard plume melt theory predicts. And ambient melt in particular is sort of the missing piece. The ambient melt away from the discharge plume is about 100 times higher than what theory predicted, and a major component of the total kind of melt budget across the terminus. And then building on this, we used actually, so the measurements from when we're sitting under the shower curtain, driving back and forth, we make measurements of velocity, temperature, and salinity, and we can assess the kind of budgets of heat, salt, and mass for the fjord upstream of those sections. And what that allows us to do is back out the total sort of bulk submarine melt coming off the glacier, as well as the subglacial discharge. And I'm really kind of glossing over the methods, which are described in this paper and a few previous papers as well. But what this lets us do is actually examine the relationship between submarine melt and subglacial discharge across a wide range of conditions over various kind of field campaigns. And so what we find, again, first in line with the first two papers that I just mentioned, the melt rates are way larger than kind of standard predictions from any variation of kind of the way that plume melt theory has been applied to measure or to estimate melt at these tidewater glaciers. And so each line here is kind of an estimate across seasons. But what we do find is that the observations do follow the theoretical scaling of melt going with discharge to about the 1/3 power. The best fit here is a 0.32 power, so pretty close, but the magnitude is way off. And so we combine these sort of like bulk measurements of the freshwater fluxes with the kayak measurements, or the autonomous surface vessel measurements that I previously mentioned. And what I'm adding here are curves that are actually suggested by entirely independent surveying of the meltwater intrusions that I mentioned. And so in this paper, kind of before we'd done this analysis on the left, we kind of proposed a few potential adjustments to standard plume melt theory of how you could kind of explain our intrusions that we were observing. And in one scenario, we said maybe you just need to turn up these transfer coefficients that relate the velocity to the melt rate. And if you do that, you get this sort of thing here, where you actually lose a lot of the discharge dependence of melt in the ambient melt regime that then ends up kind of swamping the signal. And so you end up with this very weak dependence on subglacial discharge. But if you look at another one of the scenarios we presented from the intrusions paper, we suggested, well, maybe you just need a more modest adjustment to the coefficients. And really the important thing is including the non-plume velocities. And that's also kind of the more obvious thing, that we know there are these other velocities that we were observing, and that we found a relatively energetic velocity field across the terminus. And if you think that velocity field across the terminus scales with subglacial discharge, which I'll get into in a second, you get a curve like this one here that's a bit closer to the observations. And so what kind of this first set of papers is working towards is that it seems like ambient melt away from the discharge plume is a kind of important and typically neglected source of melt, but it's still scaling with the subglacial discharge coming in here, and likely through mechanisms that allow the kinetic energy that's localized here to be distributed across the terminus. Like if you can enhance the velocities across the terminus from the subglacial discharge plume, that helps explain this elevated ambient melt. And so sort of two ongoing pieces that we're working on are, first, are we representing the discharge plume correctly? And then second, how does the discharge plume sort of energize velocities across the terminus that allow the total melt to sort of scale with the discharge, even if it's not directly driven by the discharge? And through things like waves and recirculations. How am I doing on time? Okay. Oh, okay, awesome. Okay, so first, the discharge plume piece. This is looking at you're looking at drone imagery, looking down on the subglacial discharge plume, boiling up to the surface. It's obviously a very energetic part of the ocean, and it is very localized. See also it's very muddy occasionally, although a lot of time variability in how much sediment is in there. And so one piece of our sort of ongoing analysis, this is a paper led by one of my graduate students, Bridget Oval, and we're combining here the terminus morphology, so the ice space is kind of shown in white here, the seafloor is here, and these red dots are where we are seeing the upwelling plume, and the purple vectors are where the plume is then flowing away at the surface. And as you might expect, the relationship between the plume and the morphology is going to be really important, that the plume's evolution is impacted by the ice space along which it's rising. And in this case, the discharge plume is sort of rising in a corner of the ice face here, and where the kind of the wall behind it that you can't see as well has an overcut slope, meaning that the bottom of the glacier is more seaward than the top. And that'll be important in a second. And so a big part of what Bridget has been doing is developing kind of new methods for measuring the velocity and structure of subglacial discharge plumes. So this is with ADCPs on the surface vehicles. I won't get too much into these details, but there's sort of at least two big challenges you face trying to sample these plumes. One is that their spatial scale is relatively small compared to the beam spread, the acoustic beams that are used to make these measurements with ADCPs. And so you can't sort of use typical assumptions of spatial homogeneity in the flow field that you're sampling with the acoustic beams. And so we have to kind of get creative about how we can process the data in different new ways to account for the small spatial scales of these plumes relative to that spread in the acoustic beams. And then the other challenge also is the presence of the ice face itself, which is a very strong reflector, can create all sorts of contamination problems. But we've kind of slowly over the years been developing some new approaches that allow us to see a pretty new, clear picture of what these upwelling plumes look like. For example, these are 6 snapshots of, oh, I forgot to, see this, well, I guess it doesn't work. This should be a little video, but it's not playing. But what you're seeing in these 6 snapshots here, red is the vertical velocity of the plume, and so this is the upwelling plume kind of in 6 snapshots. And what Bridget has done, not only kind of looking at the temporal variability, but also kind of the average characteristics of the plume in terms of its velocity, its geometry. These are sort of 4 slices of the plume from closer to the surface down closer to the grounding line, where the white part is the glacier, the other side is the ocean, and the kind of this blue line here is where the ice is at that particular depth. And so you can see this upwelling core with sort of peak velocities at the center, a relatively circular shape, and a velocities exceeding 1 meter per second. Okay, and one of the big results to come out of this is that the observations show about 2 times more entrainment into the plume than we expect based on standard plume melt theory. And there's a couple ways you might think to account for this extra entrainment, like adjustments you could make to the existing theory and some of the kind of issues that I've mentioned. And the first one has been proposed in previous studies, including some of my own, where we said, well, maybe this was based on observations sort of downstream of plumes after they've already started outflowing. We said, well, maybe these plumes are a little more distributed than we thought. Instead of being sort of point source plumes, maybe they're more distributed line plumes, and that increased surface area can help explain the increased entrainment we've also seen in other systems. But what we're finding here is that is not the right answer, at least for this system, because here we're actually measuring the shape of the plume as it's rising, and we can see that it looks very much like a point plume in this sort of circular fashion. We can compare it to all sorts of versions of idealized plume theory. And instead, we're kind of exploring some other mechanisms to explain this enhanced entrainment. And one of these is the fact that the ice face is overcut, as I mentioned. And so for this, we're combining our observations with some large eddy simulations. These are high-resolution models of the plumes in different scenarios where we have a vertical ice face and various different slopes to the ice face, and we can sort of assess the effective entrainment coefficient in these different configurations. What we find is between the vertical and the case with an ice slope that's closest to our observations, you get a big jump up in your effective entrainment, and you end up with a kind of plume geometry that looks much more like our observations than the kind of classical plume rising along a vertical ice face. And so we suggest, the LAS modeling suggests this is maybe accounting for about 60% of this sort of excess entrainment into the plume. The other piece, this is a little more speculative, but it seems like the extra mixing that we can't account for through this mechanism is likely due to enhanced mixing at the grounding line depth. And this is somewhat related to some of the ideas like from Earl and Alex in their papers about saltwater intrusion under glaciers. That's a little bit more exploring sort of the parameter space of Antarctica, but there's a variety of reasons you might expect sort of extra entrainment, whether it's actually getting far up under the glacier or not, but at this transition from the sort of pure freshwater in the subglacial hydrology system to the rising plume, you might expect there to be extra mixing that's very much not accounted for in standard plume theory, where really the mixing only begins in the vertical ascent. And so some further evidence for this idea actually comes from the Greenland project I mentioned, where we have better observations right down at the grounding line depth. And so these are just a few little snippets from, again, a different site, but what you're looking at are velocity down near the grounding line depth, about 260 meters, and red here is inflow towards the glacier. And so across a lot of the terminus, we're seeing this strong inflow towards the grounding line that really cannot at all be explained by our existing plume theory representations. And so sort of contributes to this idea that there does seem to be some enhanced mixing at the grounding line, under the grounding line. Where it's actually happening, we don't yet know, but I think it's an important part in the plume evolution that is not yet accounted for. And since I'm almost out of time, I just want to kind of mention briefly the some of the other ongoing work that's looking at the sort of the redistribution of kinetic energy across the glacier terminus. So what I just showed you were some results for the very localized subglacial discharge plume. But what we're finding is that the sort of important piece in this puzzle is how the kinetic energy that's localized gets redistributed across the terminus through, I'll just mention that my former postdoc, Jesse Cusack, looked at the signal of internal waves from the plume, redistributing. Okay, I'll have to show this video, and then I'll stop. Showing how we deployed a mooring up near the glacier to look at to actually get a sense for the variability, and we found a large signal of internal waves emanating from the upwelling subglacial discharge plume and propagating across the terminus. And there we are basically deploying a mooring off of basically a little barge with a trapdoor. The mooring is sitting there, and then the anchor is pulling it down. It's about to sink down to the seafloor and measure velocity, temperature, and salinity over a couple of weeks. Okay, but I will just jump to my conclusion slide, which is that we have, with this kind of combination of new observations, we're finding that melt is scaling with subglacial discharge in the way that we would expect, but the magnitude is about 10 times higher. And ambient melt seems to be this really important contributor that's not directly driven by the discharge plume, but appeals to kind of still scale with the discharge flux through plume-driven internal waves and eddies and recirculations that enhance velocity across the terminus and really sort of swamp the signal of those weak ambient plumes. And also new measurements and methods for measuring these sort of small-scale plumes, velocities, and structures. And if anyone wants to ask about it, we also have a melt stake into the ice, but I will actually want to end with one final point. Sorry, I'm going over here. I put in a bunch of videos at the last minute because I realized I was in the technology section, so I should have cut back some of the science probably. But anyway, what I'm talking about here is focusing on just one way in which kind of ocean and atmosphere warming could affect glaciers, right, through the submarine melting of the terminus. But this is only one potential mechanism or sort of pathway that ocean and atmosphere warming can affect the termini of glaciers. Another, Paul Summers will be talking about tomorrow, the role of the ice melange in front of the glaciers. And so kind of separating out these different pathways by which the ocean and glaciers are connected is definitely an ongoing challenge. Not to mention the challenge of once we know, say, the melt rates or the melange, how does that feedback on the glacier dynamics, again, is another big open question for the community. And so I will end there, and happy to take questions.
Great talk. Questions, discussion.
Thanks for the great talk. You talked about how do you observe all of the parameters that go into the parameterizations for the melt plume system, except for the discharge, which it sounds like on the last slide you get from a surface mass balance model. Do you trust that part of all of this?
Yeah, great question. So we get at it two different ways. We have a surface mass balance model, which you may or may not want to trust, and we also have from our sort of fjord budgets, where we measure velocity and temperature and salinity across fjord cross sections. We can evaluate not only the total freshwater coming through the fjord, but actually decompose it into the submarine melt versus subglacial discharge. And you may or may not want to trust that, but actually remarkably, the two independent ways of estimating subglacial discharge do line up pretty well, at least at LeConte in Alaska. I might even have a figure here. Yeah, well, you can actually judge for yourself how well you think these line up. So this is comparing the surface mass balance model for subglacial discharge with our ocean-based observational estimate. The model versus the budgets, and a one-to-one line. It did better than I thought it was going to, but yeah, there's definitely room for improvement in constraining the subglacial discharge as well. Yeah.
Thanks.
Hey, thanks. With the shape of the terminus here, I would think there'd be some kind of feedback where maybe the melt would be stronger at the bottom, and then that would tend to straighten it out over time, or is that intuition not right?
You would expect the melt to be stronger at the bottom, is that what you're saying?
Yeah.
That's sort of like the classical, if you just thought in sort of like the classical plume melt theory scenario, you do get your highest melt rates predicted near the bottom. But actually what we're finding at LeConte is that it's overcut, meaning it seems like the melt is higher, or something's causing the ice to be further cut back towards the surface.
So that means it'll stay overcut because the plume is continuing to melt it that way.
If you think, I mean, well, this is where separating out the role of submarine melting versus calving is tricky, because how much is calving contributing to the shape of the ice face versus melting. But one thing that we're finding as we are now able to, with the profiling ROV, we can actually kind of assess the velocity field near the ice, kind of inching closer and closer. And we do find that the kinetic energy in the upper water column is much higher than down deep, except in the subglacial discharge plume. So like if you care about this sort of across the whole terminus, there's overall higher velocities and presumably higher melt rates towards the surface, actually, in this case. I think likely because you have the most kind of internal wave energy and eddies and recirculations in that surface layer. So yeah, cool.
And maybe just one more quick thing. So if it was tilted the other way, if it was, overhanging, would the melt be closer to the theory or even smaller, or it's always bigger?
Well, so in places like we have ice morphology from other tidewater glaciers, and you do often see these that undercutting, but importantly, we don't actually have the melt rates from those systems. And so it's often presumed that the melting is causing those undercuts, but I would say, and it probably is to some extent, and that's a little bit more in line with sort of what you get just from plume melt theory, but we don't have the melt rates at those systems to actually be sort of directly putting it together. Yeah.
Thank you.
Justin kind of, well, first, wonderful talk. Thank you, Becca. Justin kind of took my question away, so thanks for that. No, but it's amazing. Like, I always thought that in the plume it's undercut. And so, we did this work with Donald and Fiamma at Sakhaliob, and we had the multi-beam, and essentially it was overcut everywhere, but we didn't have the data in the plume.
Yeah.
And I always assumed that in the plume it was going to be undercut.
Yeah,
and so maybe it's just wrong. Yeah.
Yeah, but I will say, in our Greenland data, which I only showed a teeny snippet of, there the biggest plumes do have these sort of cave-like undercuts. Okay. So I think now that we have the kind of these combined observations at two sites, I'd say it seems like both things are happening. Or yeah, it's not all one or the other. Yeah. In KS and West Greenland, you're seeing more of a classical undercut cave type feature.
Right. So I was wondering whether there might be a dependence on the temperature of the water as well at the base, right? The warm water that comes in.
Yeah,
right?
yeah. Or another hypothesis too is in this system where you have so much subglacial discharge coming in, so much energy, it's being pumped in as subglacial discharge, but then it's getting you're sort of trapping all of it in some of the stuff I didn't really show in these internal waves and eddies and recirculations in the upper layer, and really enhancing, I think, melt in the surface. But at bigger glaciers where that kinetic energy is a little bit diffused across the whole terminus, you maybe don't have that effect quite as much. This is really concentrating a lot of that kinetic energy that I think gets trapped in the surface layer.
Yeah.
Yeah.
Cool. Great.
Yeah.
Thank you.
All right. Awesome talk, Becca. So in the traditional plume theory, you kind of assume that you have this infinite reservoir of water of a particular temperature and salinity, right? And then it's a question of just how much you're entraining it, what's happening inside the plume. And I guess in terms of thinking about what's going on outside of or away from the plume, what do you think the role of detrainment is? Because that's not in a traditional single integral plume model. There's no detrainment happening. You're not tracking how the far field is being modified. Do you think that that's important?
So you're thinking of detrainment from the main discharge plume?
Correct.
Yeah, so we do have a lot of CTD profiles from both within the plume. Well, I shouldn't say that. We have a few CTD profiles from within the plume and a lot from right outside. And I would say we see no real signal of detrainment from the subglacial discharge plume. Until you get to the surface layer, where then there's all chaos breaks out. But for most of the rise, we have all these. We do see a lot of intrusions that have the signature of submarine meltwater mixing directly with the ocean, which we attribute to these ambient melt intrusions that are just submarine melt mixing with ocean waters. But you really, yeah, observationally, I'd say there's not much evidence for it, or if it's happening, it's then getting entrained back in very quickly. But that it's not significantly modifying that kind of pool that is getting entrained, as far as we can tell from the observations.
Thanks.
Yeah.
Awesome talk. Thanks a lot, Rebecca. At some point, you showed the LUTS like photography. I think it's like on glacier, and you don't have to go to it, but it was quite difficult kind of to estimate the timing. But essentially, icebergs just like flopped over. And also for the Greenland, you showed that picture, static picture with plenty of icebergs. So I was just curious why is that extra 40% of mixing could be just mechanical. You have all your icebergs falling off, mixing stuff around, and like, do you really need to find that extra 40%? Or as a question, could it be kind of quote unquote external to the plume theory on like the oceanography stuff, and you just mechanically add all this?
Yeah. So yeah, definitely iceberg-driven mixing and velocities are super important. And actually, there's two papers coming out that I'm involved with. One using a fiber optic cable in South Greenland, and one using actually the mooring data that I showed here. Both kind of trying to quantify both the mixing driven by these calving events and just the velocities across the ice space that might be important. So I think both of those papers point towards it being important but not dominant. And I think like in the work here, I would say we are biased to like the work here, like where we're quantifying the entrainment in the plume. That's effectively a pretty short snapshot. Like even the plume is rising very quickly. We're looking at it over. This is maybe actually averaged over an hour or something. But we do have a bias towards getting these observations when there aren't big calving events, because when there are, we like run away. Well, I think, and then we have from the moorings an idea of how quickly that energy is dissipating, and it's on the time scale of an hour or so. So I think we definitely are biased towards sampling when there isn't a ton of energy from the icebergs in the surveys, although in the moorings we are trying to quantify it, and I think it's important but not dominant is my guess right now. Yeah.
Awesome. That was really cool. I am following on from, Till's question, I guess, about the undercutting, overcutting situation. And I guess I'm just hoping for a bit of context. Do you know that this plume was here for a significant amount of time prior to taking these observations? Like, do you have some history of the plume?
Oh, great question. So we have, well, yes and no. We have a lot of we've been working, we've had sort of 6 years of field campaigns, and within those we've had a couple, some years we've had multiple campaigns, and like this plume, it seems like it was in this location from, I want to say across like 2 different field campaigns. So we definitely do see persistence on a time scale of months and sometimes year to year, but then especially when there's significant changes in the terminus position between surveys, then where the discharge plume comes out often seems to be routed very differently. So I would say like this plume seemed to be consistently in this location for, I think, at least the whole melt season.
Cool, that's helpful context. Thank you.
And it was the kind of only one we could find at this time.
Right, thank you. This is a very naive question probably, but in your schematics you always show a very thick, relatively thick plume and a very thin boundary layer close to the wall. I would have expected the boundary layer to be as thick as the plume because everything is turbulent. Am I missing something there?
I think it's just a question of how you're defining, how you're defining your boundary layer. Because and this is actually, I think, a big source of confusion sort of in the literature. Like, is the plume part of the boundary layer? Right. Is it the boundary layer, or is the boundary layer within the boundary layer? And the way that this is conceptualized is really oversimplified, right? To I don't know if I should go all the way back here, but this picture of like a uniform velocity in a plume with a boundary layer within it, that's way oversimplified. And you can see actually in the LES simulations some of that structure that we expect and that we kind of do see as well. Oh, I shouldn't have gone back and then forwards. Let's see if I'll get there. there we go. So you can see, yeah, some of that structure within the plume in the LES and to some extent in the observations. And interestingly, once you bring in this overcut slope, the structure gets even more complicated where the core of the velocity is off the wall significantly. And yeah, how you define your kind of inner boundary layer, and then there's the inner turbulent boundary layer and then a viscous sublayer. And so, yeah, it's sort of a question of...
Would that change the melt rate, the scaling for your melt rate at the end of the heat transfer, essentially, between the outside of the plume and the boundary layer? If you take the entire plume to the boundary layer? I don't know.
Well, then in this whole framework, like, so if you're kind of working within the framework of these melt parameterizations, you need a velocity that is driving shear-driven transfer across the boundary layer. And so if you took your whole plume as a boundary layer, then you wouldn't have a velocity to force your boundary layer with. I mean, except the external velocities from other modes of circulation. Okay. But this is, you're definitely getting at sort of like a really important sort of blurred line in how we represent this that is not, I think, in some ways, it's, ill-posed in how we do it, yeah.
All right, thank you. Let's thank Beck again. And also let's thank all of our speakers for such a great session.